Thank you very much, Kieron. Really interesting. Thank you. So questions, I guess, from the theorists. So if you either raise your hand or just turn on your in the chat.
So maybe a quick question, Kieron, that's not related to your work, but to the last paper. What do you mean by how they calculated the dissociation curve? You mean spin open or spin restricted? Or...
Exactly. So the description in the paper, even in the supplementary info, is kind of a little cryptic to me. So I can't tell if it was a sort of regular cone sham calculation. And yes, like is H2 a Singlish, right? In the calculation.
I'm pretty sure, right? I mean, I guess they made it spin open. I mean, that is, it's not a singlet, not a proper. I guess they used this a spoiled singlet, so to say, incorrect singlet, if you want, or however you call it.
I think so too, right? But,
yeah. Okay. You think so too? Okay. Yeah.
But okay. You know, I'm just not sure. Right?
Sure. Absolutely. No question. Yes, I didn't.
So Aaron will talk to us on Friday and or Thursday, and I'll get him to explain it to me. Yeah. I mean, I don't think there's anything wrong. It's just I just can't.
And can you briefly? I mean, so you don't use the density directly, if I understand. In your cases, the density is only used via the cone sham regularizer. So you don't put in the density the exact density that you probably also got from the DMRG. Is that correct, or did I misunderstand?
Well, so in using the cone sham iterations, the unconverged, as it's doing the iterations, we only use the energy, and we use the energy error sort of going backwards in iteration time, for about 15 of the previous iterations, weighting them less and less the further back you go, because you start off with big errors, you don't want them to dominate. But then at the end, we use the density in the loss function, the cost function. So we are training to get the densities right.
So you need, in principle, for your training, you do need the exact density as well.
Yes.
Okay.
Yes. I see a hand up. There's some young.
Yes, Anatol.
Hi. Yeah.
Yeah, I was asking the question here. Go ahead, student.
Thanks for your talk. Can I conclude from your decision to pursue and from the discussion of the science paper and from what the work you presented, that you have abandoned the orbital free DFT idea using machine learning, or is that still something you would consider an interesting question?
Oh, well, there's two aspects to that, right? So no, I wasn't saying that we abandoned it. We still have a lot of projects going in that area. It was simply that today I was focusing on this exchange correlation stuff and the strong correlation in particular. So there's still these sort of two aspects. So okay, so the fact that people are able to make these force fields in some sense bypass the need for the orbital free functional. However, right, I would say in some sense the jury is still out as to what happens, especially when these force fields run into a place that their training has not prepared them for, let's say. And sometimes they can go very, very wrong. And so you need to maybe insert some more data to train on. So it's still interesting, I think, to try to find an orbital free functional just for its own sake, because it does give you the density. And then the other thing is, when we learn stuff about even the kinetic energy for orbital free DFT, it also then tends to teach us stuff about exchange correlation. So
Right.
tricks that work for one can often work for the other. And in fact, in some ways, some people would regard it as a harder problem because you have to have higher accuracy, that kinetic energy functional, but then other people would say it's an easier problem because it's not a many-body problem. It's not the exchange correlation piece.
Right. Thank you.
You're welcome, Anatole. And, yeah. Will I see you later today, as it were?
Yes, of course.
Great. Okay.
Georg Madsen.
Yeah, thanks for the talk. It was very interesting. It was just to follow up on the other Georg's question there. So you learn on the energies or you have a loss function. I think you also had in a slide with the density and the energy. So when you're comparing the densities, you're sort of comparing a distribution, which is not always or two distributions, which is not always a trivial thing. There are many ways of defining a distance between two distributions. As what did that mean for your results, or was that a key to your result?
So I think that was the L2 norm, right? Was, that's what people generically do. The difference of the square integrated, right? So some measure of the difference in two densities. So in fact, we spent quite a lot of time playing with various other ways of measuring that difference, and also the sort of relative weight of the density contribution to the loss function versus the energy contribution. And this is the kind of thing that tends not to appear in this is a perfect example of the difficulties of machine learning compared to our regular standards. So I drive the students nuts because I ask all these questions of, well, I want to vary these two, and I want to see how it depends on these details. This is, right, a perfectly normal sort of scientific question. Does it really matter, right? So in fact, they did lots of experiments. They call them experiments on the computer. And in the end, we found, sort of as I expected, we were in a sort of plateau region. So as long as you didn't make the relative weights of the two contributions too big or too small, you got essentially the same answer. But to do those experiments was very painful because they have to do the optimization, right, every single time. And so, you couldn't possibly do this in one of these bigger calculations, right? It was only because we were doing these 1D relatively simple systems. And this was just one of a dozen questions that I had about probing what's important in the calculation. You do you sort of intuitively write down an algorithm that you think will work, you try it out, and hopefully it does work, right? But then why did it work? And you can spend like years probing, doing numerical experiments to find out what depends on what. In the meantime, of course, all your competitors have published 6 papers. The kids, have either gone and found a less demanding advisor, or they've quit graduate school and gone straight to work for one of these high-tech companies, right? So we do a little bit of this when they are sufficiently, mad at me, then we stop, right? And that's what, right? So yes, so there's a little bit of that in this paper, but it's very hard to actually do the stuff you would normally do because You know, the world wants results quickly, and whether, you know, I don't know for sure that it's a good idea to hold everything up while you try to understand the way you would normally try to understand what is going on in these things, right? The value is if the algorithm is useful and working, other people will try it out. The finer details will be worked out later if it turns out to be something that people can use, which is the more important question at the moment, right? Yeah. So this version of the paper, which should appear on the archive within a few weeks, and it has a bit of that, right? Not as much as I wanted, but as much as my students could stand. And they are very, generally speaking, they are very patient with me until they're not. Yeah.
Thank you.
Sure.
Are there any more questions?
I guess there was a lot of stuff. Yeah.
Yeah. I still. So I had a question with this H2. Okay, you know, I know nothing about these things, but if you have this so it's a one. I understand this solver was a one-dimensional row of hydrogen atoms, right? So but if physically, I can understand you have two hydrogens and then you have two H2 molecules. Does it mean you really look into weak interaction between two molecules, then trained on the strong interaction between two hydrogen atoms? Do you understand this correctly? Okay.
That's right. So, but I'm trying to remember. So for that one, I think we trained on H2 and we trained on H4, meaning all the separations are identical in the H4.
Okay.
So we had near equilibrium H4 and stretched H4.
Okay.
So we just had those, I think we had those four, and then we were able to get H2 interacting almost, not quite as good, but almost as good. So that was quite a surprise.
Right.
Now the curve I showed, because it's one dimension, they don't actually, so there'd be a van der Waals binding of those guys, which doesn't happen, I think, in 1D, but it doesn't matter for the principle of the thing. It's how accurate can you get the curve.
Okay. Yeah, that's interesting. Okay, Stefan.
Yeah, so I have a question about the automatic differentiation. I wanted to know, so you use the previous iterations from solving the Grosjean equation, and I wanted to know how can you quantify how much additional information there is with respect to just using one iteration, and if it is, how useful the additional information is that you get.
Right. So in a sense, it's not using it directly quantitatively. What it's doing is kind of guiding it toward the sort of ultimate stationary point that it's going to find. So okay, so first, the differential programming is just this general term these days for machine learning algorithms where you can differentiate everything. You're sort of using basically the elements of the original calculation to calculate all the derivatives. I think very analogous to the way quantum chemists want to get as many derivatives as they can analytically when doing molecular calculations. So that aspect is just there to make things very efficient, so then you can play lots more games than if you're doing if you don't have it. Okay, so the iterations, what they're doing, using the iterations stops it from kind of going toward any sort of what we would consider an unphysical solution to this problem. So what it's doing is you can use the iterations to you know, well, so it's this general idea of regularizing, but usually when you regularize, you put in an extra piece to the cost function, right, that balances and stops it from overfitting. Here, this is like an extra procedure, which is sort of stopping it from finding some sort of, let's say, crazy relation between energy, you know, that happens to fit, right, that, you know, that gives you some sort of minimum, but is very overfit to the specific situation because it's seen a bunch of situations. So it, you know, whatever fit it's ultimately going to develop, it's going to be one that doesn't do too badly for these many different cases. So I don't know, for example, if you trained it with, so these are sort of different cases, but somewhat similar to the one you're trying to find, right? So it's sort of exploring the density space near your problem as well as the solution to your problem. So in a regular DFT, you say you're training a functional with empirical data, right? You actually only ever use the converged cone sham solution, right? That's what everybody does, right? But actually, when we so this didn't work without it, without the including the iterations, and we also discovered it didn't work if we just included all the iterations. And we ended up with this thing where we just do the last 15 because it has to be able to forget about the bad ones. So presumably in your initial guess, which is all bad, it's too crazy, it's too different from the problems you care about. And so you don't want to regularize on those ones because they're not relevant.
So it depends. So what do you use as the initial guess? Is it atomic densities? Or?
I think it might have been overlapped atomic densities. It was something pretty bad.
Yeah.
And maybe we had no functional, right? No exchange correlation. So, you know, those first iterations, but, you know, it does find its way, right? So, you know, yeah, you've no functional, you've overlapped atomic densities. So it's doing some kind of Hartree kind of calculation. But even then, so every time, you know, every cone sham iteration produces an example of cone sham potential and density that are a pair. They're not the solution to your problem. They're not even, you know, the converged cone sham solution to, you know, whatever functional you happen to have, but they are a pair, right? And so that's what's, you know, presumably stopping it from you know, going off in some crazy direction. Yeah, that's the best I can do.
Okay, thank you.
Because my students wouldn't spend long enough.
All right. Are there any more questions to Kieron? That's not the...
Wait,
no.
Herman Alexander.
The one? Oh, yeah. Alex.
Okay, thank you. Very nice talk. I enjoyed it a lot. My question is, I mean, from a chemical sense, about this rotation of the OH group, where you said you learned the delta between DFT and couple cluster, but you said it doesn't generalize well. But as a chemist, I would expect it to generalize. Is there a particular reason why it doesn't?
Well, so by generalizing, I mean that the functional that we have, you know, you can't then give it, you know, a totally different molecule and expect it to work. So it is trained on many configurations of that molecule. Now we did a little bit of testing on the smaller ones. I think it was ethanol and something else, and we showed that in fact it does generalize a bit. Mm-hmm. So I remember trying to figure out what requirements are. So, and so now I can't remember. Maybe it was ethanol and methanol or something.
Mhm.
So let's say it was those two. You can look at the paper. So let's say you have 2,000 training configurations, right? So you can do 2,000 of molecule A, 2,000 of molecule B, and you get a certain error for on the test set for each of them, right?
Mhm.
Or you can do 1,000 of A and 1,000 of B,
Mhm.
and so it's learning sort of both of them, and it does better than 1,000 of A or 1,000 of B, but
Mhm.
not as good as 2,000 of A.
Mhm.
So it was actually generalizing a bit,
Mhm.
but it was not such that you could just go off and feed it some other molecule and expect it to work. You would need to retrain or further train.
Okay, thank you.
That's the sense in which I meant
Mhm.
that. Yeah. You're welcome.
Right, thank you. So I suggest we all thank Kieron for a really great talk.
But don't forget to invite me back for real.
I know, we will talk about it when we meet.